Yesterday we focused on some aspects of probability. Specifically, we were asking that if you take n realization of some random variable and add them together, then can we say something about the sum? And the way we went about was that we first did a specific case of random walk where the probability distribution of the individual summand was either +1 or -1. Then we added them together, we got a Gaussian. Then I showed some numerical results that if you generalize the random walk problem, not just single step, but 5 steps, Gauss, continuous and so on, the answer does not change. And then I stated the result of why this was true, that there's something called center limit theorem, which says that when you average over microscopic length scales, which corresponds to summing over a large number of variables, then that leads to the concentration of the values of these averages. Okay. And roughly speaking, it said that if y was a sum of n random variables, then the value of y typically is the mean times n, and it varies as sigma times root n, plus minus sigma times root. This was the statement of central limit theorem. Or if I take these readings and divide by n, then you get a mean plus minus the error going down as root n. Okay. So I skipped over the derivation. I thought that was not necessary, but then I thought, let me just derive this central limit theorem for a general, not random walk alone, a general problem. So just to set the problem, so we had a variable y, which was the sum of these random variables with the mean subtracted out and divided by the standard deviation times root n. The mu was the mean of each xi, and sigma square was the variance of each of the distribution. And the question was, what is P of y? Okay. So let me do on the board this calculation. And so we are interested in P of y. So let me write. And I want to ask, what is P of y? So whenever you have some quantity which is a function of many random variables and you want to compute its probability, you just have to sum over all the realizations which lead to y, and that is the answer. Okay, so which means I do integral over dx1, dx2, dxn. Then for each realization of x1, the probability is small p of x1, small p of x2, p of xn. They are a product because they are independent. That was our initial condition. But all values of x1, x2, xn don't lead to y. So when I do this integral, I have to put a delta function, delta of x1 minus y. Okay, let me use small y, that is easier, small y. So that is the thing. If I had some other function here, if it is product of xi's being y, I just put that constraint there. Okay. So I want to do this particular sum, but when a delta function is there, I clearly cannot do that easily. So what should I do to remove the delta function? If I have some, like in, is there some trick I can do to remove? Yeah, you do a Fourier transform. So let us say I do integral e to the power I k y, p of y, dy. I do this integral. When I do this, so this becomes dx1 dxn xn e to the power I k, and wherever y came, I just replaced by this quantity. It is x1. Okay. So now we are left with, once I do this, I'm left with n independent integrals. They are not. So I first pull out this one, e to the power minus I k mu root n sigma. That is this I k into this last quantity, and the remaining is integral dx p of x e to the power I k. Right, they are all identical integrals. Okay. So I want a notation for the Fourier transform. Notation will be p tilde. So this will be p tilde of k, and this will be therefore equal to e to the power minus k sigma small p tilde, but k is now a bit different, k by sigma root n to the power n. Is this clear? This here minus. If you want, I can put a minus. Whether I put ik or minus ik, it is okay. Okay, in the notes maybe there's minus ik. Okay, let us put minus. Ik is enough, so that it is just not exactly on the. Okay, so so we have now got an expression for the Fourier transform of this variable py, and there's a name for that. It's called characteristic function. Okay. When I do for a probability, it is called characteristic function. So now I want to know how this will look like. Okay, so let me copy that p tilde of k. Remember, your small p tilde is an arbitrary probability distribution. Okay. So let us look at how a general, so p of x e to the power I k x. This is my Fourier transform. I can do this I can do an expansion here. Integral p of x into 1 plus I k x plus so on. I do an expansion for e to the power I k x. So this becomes, first one is p of x into 1 integral, which is 1 plus I k expectation value of x, which is mu, minus I square I k the whole square by 2 factorial plus x square average. In general, I k to the power n by n factorial. So that is how the Fourier transform looks like. And then if I take logarithm of this, so if I take log of p tilde of k, this is equal to log of this whole quantity So log of 1 plus y, which I Taylor expand as y minus y square by 2. We have been doing this all the time. Where y is this whole quantity, so this becomes I k mu. Second one is plus I k whole square by 2 factorial square plus higher order terms minus y square by 2 minus I k whole square by 2 mu square plus I k the whole cube and so on. Okay. So I just kept the terms of order I k the whole square. There are other terms also there. So this becomes I k mu plus I k x square minus mu square is what we defined as sigma square. The remaining ones I will write it as plus I k cube factorial. There is some word people use which is x cube cumulant plus and so on, x to the power 4. That is the expansion for log of p tilde of k. It's called a cumulant expansion where this is called the first cumulant, second cumulant and higher order cumulants, okay, whatever that be. But that's how the expansion looks like. We are now going to substitute that expansion for this into this expression. Okay. Okay, so we had derived up to here. So I take log of p tilde of k plus n times logarithm of p tilde of k by root n. But that expansion we know, it is this expansion. But I have to replace k by sigma root n. That's the only thing I have to be careful of. First term is I k mu. I k mu is I k by sigma root n. Second term is I k the whole square by 2 factorial plus I k. But k I have to replace with k by sigma root n, k by sigma root n, the whole square, sigma square. Third is I k the whole cube plus I x cube cumulant plus. So if I want to know the exact answer the right answer for p tilde of k, I need to know all the cumulants. Now the first two terms cancel out. Then I have to look at the next term, which is minus k square sigma square by 2. This n and this n okay, the sigma square. I didn't like that sigma square. Okay, we'll figure that out. Plus, the next term has 1 by n to the power 3 by 2. So it is order 1 by root n. The next one is order 1 by n and so on. K square by sigma square into sigma square, sorry. Okay, so I've just done an expansion and I see that the first term is independent of n. The next one is order 1 by root n. So when n goes to infinity, this goes to 0. this goes to 0 and so on. And I'm left with an answer which is minus k square by 2, which is independent of the initial distribution I started with. So your p tilde of k is e to the power minus k square by 2 when n goes to infinity. So that is the essence of central limit theorem. It says that your sum, okay, one more step is remaining. Which function has a characteristic function which is Gaussian? So let us say p of x is e to the power sigma x square by 2 sigma square into 1 by root of 2 pi sigma. This is normalized to 1. I take its Fourier transform. So p tilde of k is 1 by root of 2 pi sigma e to the power minus x square ikx. This I can complete the square. So I can do, okay, I will not do this. This calculation I leave to you. If I complete the square and take the answer, I get an answer like this with sigma equal to 1. So this exercise I leave it to you. If I do the Fourier transform, inverse Fourier transform, I get e to the minus x square by 2. Okay, so that is the derivation of central limit theorem. Any doubt in this? It used the fact that n goes to infinity in dropping these higher order cumulants. Okay, so that was this was that, this was this. Okay, so now as we promised, now we will leave this probability aspect and go to asking, can I look at the working rules for doing calculations in StatMech? Now there are two approaches. One approach is to spend time motivating and deriving them. Other aspect is to take them for given and apply to interesting systems. Okay, so when you do in your course, you will spend a lot of time trying to motivate why certain rules are there, but we will ignore them. We will state those rules and then try to apply them to interesting systems. Okay. Now, when you apply them to whatever system you're interested in, there are some of them for which you can do simple calculations, but most of the time you cannot do those calculations. Then we have to do them on a computer sometimes. So we will do both. We will do some examples with simple calculation, and then I'll tell you how to do on a computer. So I feel that with this much information, you can actually take any problem that is of even what you see around and do something new with them. Okay. So before going for the going towards the rules, I'll do one slide review of thermodynamics, which I. So firstly, I have some thermodynamic system like a gas of container of gas or some water or some. How many parameters are required to define fully or parameterize fully a thermodynamic system? 4? Sorry, any 3? That depends on it clearly depends on the system you're interested in. But given a system, how can you figure out how many are required? So for example, if I want to specify the state of a gas, how many things will you specify? Pressure and, if I measure pressure and, for example, if I say pressure and temperature, is that enough? Or should I say pressure, temperature and density? How many things should I measure? If I say pressure and temperature, then density gets fixed, right? Its rho gets fixed. So the answer is that there should be n plus 1 parameters, where n is the number of ways of doing work on the system. For example, the pressure for a gas, the way of doing work is through compression or expansion. So that corresponds to pressure or volume. And temperature is another way of supplying, let's say, heat to the system. Okay, 2. Now, whatever that may be, so then there's first law of thermodynamics, second law of thermodynamics, and all those things. But after all that, there is one fundamental relation in thermodynamics, which is there's another heat is also there. So heat so you can do work in mechanical, magnetic, and so on. In addition, you can supply heat by some other means, by heating it up, for example. That's the next variable. So there is first law, second law, and so on. But there is one fundamental relation one must remember. This is the relation that governs your state variables in your phase space. So your phase space may be defined by pressure, temperature, and so on. And now you ask, if I go to a nearby point in phase space, how does energy change, for example? Okay. Now this does not depend on whether it's reversible, irreversible, or not. It just says that if I go from one equilibrium state to another equilibrium state, how does the variables in the state space change? And that relation is, if I look at the change in internal energy dE, this T times TdS minus PdV plus mu dN plus SdM plus sigma dL. What are these quantities? So dE is a change in energy, T is temperature, ds is change in entropy, P is pressure, volume, so that is PD, work done. Mu dN is chemical potential, N is number of particles, mu is like the work you do to change the particles by 1. H is like magnetic field, magnetization, sigma is like surface tension, dl is this, and so on. So if you have some other system in which some work is done some other way, sigma times stress times strain, you could add that also. But this relation is a fundamental relation in thermodynamics. We will need that relation in our calculation. So even if we've forgotten how it comes about, this is how it comes about. Okay. So just to remember, TdS is like your first law, but remember that this is a relation connecting things in phase space. But if you want to remember in some way, this is like dq and this is like pdv, dq plus dw. But it is not that work done is always pdv. That's only for a reversible process. But this is not. This is to connect things in state space, the variables in state space. Okay. So with that relation we'll come to again. So I'll keep showing that relation in case you don't have to remember. Now, remember in statistical mechanics we are going to we need to know how to assign probabilities to each microscopic configuration. Once I know that, I can calculate things for the macroscopic quantity. That is our aim. So aim is how to give rules for assigning probabilities. So I'll set the primary rule. Rule number 1. So I take a system which is an isolated system. When I say isolated system, what I mean is all the extensive quantities like energy, volume, number of particles, magnetization, they're all given. They're not changing with time. Okay? So that will be an isolated system. For such a system, all microstates that have a given E, given V, given N, given M will have equal probability. That is that you should state as a hypothesis or a rule number 1. So let me state again, all the states consistent with a given macro state are equally likely. So then what to do with rule 1? So one thing you can say is that if I give you a particular microstate, what is its probability is 1 by number of microstates, because they are all equally likely. There are omega of them. So 1 by omega is the probability of one microstate. So when I make one observation, if I were to track one microstate, I'll see the probability 1 by omega. So since that's the only thing to calculate, we first calculate omega. But after that, what? Okay, so is this part clear? This is the rule number 1. So I have calculated omega. Then what do I do? Then I need some addendum to rule 1. I need to know what to do with omega, and that is the connection to thermodynamics, which also we will take as a given. Entropy is k log omega. Okay, so if I start with the microscopic configurations, I compute omega. From there, if I take a logarithm, I get a macroscopic quantity omega, entropy. These two rules we will take as given. Okay. So let us do some examples to see how this rule works. So first, a standard example, which is you have a box in which there are n particles, V is fixed, energy is fixed. Let us say an ideal gas, and I will do in d dimension, a d-dimensional ideal gas. So now we want to know the number of these. Here E is a continuous variable, so I will be careful how to define number of states. So I will define the number of states corresponding to NVE such that omega E dE is the phase space volume of energy between E and E plus dE. Okay. So I look in the phase space, I look at the volume that corresponds to energy E and N and V, both, all three put together. So for ideal gas, what is my energy? I have no potential energy, I have just kinetic energy, P1 square by 2m plus P2 square by 2m plus Pn square by 2. Then I use the same trick we did here. I want to compute the volume corresponding to a certain energy. So I integrate over all the degrees of freedom, x1, x2, xn, momentum 1, momentum 2, momentum n, they are d-dimensional, but with the constraint that when I sum over all of these, I should get E. N is already constrained, V is already constrained. Okay. So this is my integral. So how to do this complicated integral? So one may say that this is the surface area of a dn dimensional sphere of radius r or E or something. It is you are looking in how many dimensions are there. This integral has d for p1, d to p2, so the d times capital N. So it's a sphere of dimension dn. Of that, we are looking at the surface area of something. So there is some formula for that. That formula is complicated. We don't want to look at that formula. Okay, maybe we can do the look at the formula, but let us do the integrals one by one. So first, do the volume integrals, which are free. I mean, integrating over dx1, it gives me a factor volume. I do ddx2, I get another volume. So I get v to the power n when I do this much integral, and I'm left with the momentum integrals. So let's not do the integral. Maybe we don't have to do the integral. We need to know the dependence on volume and energy. Okay. So let us do a trick here. If everything okay, I'm just doing an integral. So if I redefine, I want to pull out this E from this delta function. So if all these factors had a E, then this E would come out. So if I define pi square as some root of 2me p tilde of I, because when I take pi square, I get E times p tilde of I. So if I'm going to do this substitution, I can pull out this E from the delta function. Okay, so I'm going to do that one first. So I have this particular, maybe I should do in the, no, it's okay. So I come back to the integral, I'm going to scale out the energies. So for each of the dpi, when I do dpi, I get root of 2me dp tilde of I. So there's a factor of root of 2me associated with each of these dp's, and there are dn of them, so I get d times n, where d is a dimension. Then I have an integral over p or the p tilde. The delta function I pull out a 1 by e. Okay, and then that is it. So I get some answer. Omega is v to the power n, e to the power dn by 2 minus 1 into some constant, not constant, some factor gamma which has neither volume nor energy in that. It has some mass dependence, it has some other dependence and so on, but it has neither V or E. So we need only this much. Once we have this, so we have computed our omega, not fully in terms of some unknown constant, but we look at rule number 2. We ask what is entropy? Entropy is log omega. So when I take log omega, I get n log V, dn by 2 minus 1 log E, plus log of this gamma which I have forgotten. So we have computed the entropy. So that is what, no, we started with ideal gas, and now we have got a macroscopic quantity, the entropy, from here. Then what do I do with that? Now I go back to my fundamental relations of thermodynamics. I go back to this equation. dE is TdS minus PdV plus mu dN plus HdM sigma dL. And I look at this expression and I ask, if I do del S by del V at constant energy, constant number of particles, then I get P by T. Or, so P by, so that is 1. So, but I know my expression for entropy. S is n log V. So I differentiate with respect to volume, n by V. So I get n by V. So that is my P equal to rho T, which is my ideal gas equation of state. Okay. What about, I look at this equation, I do del S by del E at constant volume, constant n, constant whatever. Del S by del E at constant volume is 1 by T. So I go back to this expression, I differentiate with respect to E, del S by del E, I get dN 1 by T is equal to dN by 2E, or E is dN by 2 into T. Is that right? For each degree of freedom you have half kT, so the answer is that. Okay. So we took the rule number 1 and its associated connection to thermodynamics and applied it to ideal gas from the microscopic picture, and we got the answer we expected. Is that okay? Okay. Now let us do another example. Suppose E was not P square by 2m, but P to the power 4. So if you understood the previous example, can you tell me what will change? Take 2 minutes and tell. So we did the calculation earlier where E was P1 square by 2m plus P1 square plus P2 square by P3 square. Now I am taking the ideal gas meaning no interaction, but your energy is P to the power 4 summation. So what changes? Will the equation of state change? What will change? Just try it out, try the calculation. Anybody has any guess? First, what about the equation of state? Huh? Equation of state is not changing, is some answer. Will energy change? 2? Okay. So for me it is very easy to do because I can just copy the formulas from the previous page and modify them this one. Okay. So if you have thought a little bit, it might be easier to follow. So your omega now, the integrals over dx don't change. So they become v to the power n. The integral over dpn I have rewritten. Delta function changes. Instead of p1 square, now I have p1 to the power 4, p to the power 4, pn to the power 4. So if I do the substitution, pi is e to the power 1 by 4 p tilde, that allows me to pull out the e, but instead of dn by 2, I get dn by 4. That's the only difference that comes. The remaining things, there is some other constant that comes, we don't care about that. So now your omega has become v to the power n, e to the power dn by 4 instead of dn by 2. So if it had been 6, I would have got 6 here. Okay. So I can do the problem for any dependence of E on P. Now now I connect to entropy. Entropy is log omega n log V plus dn by 4 log E. and now I do my standard differentiation now. So once I have my entropy, I can do del S by del V, del S by del E. Okay, so back to the same rule, del S by del V is P by T, del S by del E is 1 by T. From this fundamental relation, I can get these two. When I differentiate with respect to volume, del S by del V is back to the old answer, N by V, I get back ideal equation, ideal gas. Del S by del E, I get dN by 4E, so energy has become dN by 4 times. Okay. So the ideal gas equation of state will not change unless I put some interaction. That is the moral of the story. I can put whatever relation I want between E and P, it is not going to modify the equation of state because it is non-interacting. That is okay. If that is that was clear, is that clear? Okay. Now let us change our system because I like and we will do some things which are discrete. So let us look at some discrete system. So discrete system, when I say, let me define the problem for you now. So now I have not V volume, but V sites, site number 1, site number 2, site number 3. These are lattice sites up to V sites. And I have N particles. Okay. And they don't interact. So I can put the N particles wherever I want, and all the configurations will have equal energy. Is that okay? What is omega for this? Omega is the number of microstates. Okay. Anybody else? What is the number of microstates for this problem? I have V sites and N particles. Sorry? Who was saying? What is that? They have no interaction, meaning no particle sees any other. What is NCV? Why is that? Yeah, but there is no interaction. Two particles can be on the same site also. The problem I have stated has no interaction. N power V or V power N? What is the answer? V power N. Okay. So let us look at the answer. The first particle you can put in any of the V sites. How many ways can I do that? V. Second particle, V. Third particle, V, and N particle. So V into V into V into V, V power N. Okay. So now we again apply the rule. We have completed the first one. We apply the rule again. S is K log omega, which is K into N times log V. I differentiate with respect to V, del S by del V, Kn by V, but I know that del S by del V is P by T, so I go back P equal to rho K T. So ideal gas, this is ideal gas on a lattice. Previously we had done ideal gas in a continuum, now we got ideal gas in a lattice. Okay. Is this okay? Next one. So now let me introduce some, those particles were distinguishable. Now let me introduce some indistinguishability. So I have 1, 2, 3 up to V sites, N particles, but they are now indistinguishable. I do not know which particle, I cannot distinguish between two particles. So, and I give you all configurations of equal energy. There are no interaction, but they are indistinguishable. What is omega for this? V power n by n factorial. Why? Okay. So one answer is V power n by n factorial. Okay, let us see whether that is true. Okay, so one answer is V power n by n factorial. Any other answer? Let us take V equal to 3. 1, 2, 3. So V equals 3. And let's put n equal to 2 so that we can count them. One case is first particle is one particle here, 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 one particle here. That is 3. One particle here, one particle here, 4, 5, 6. Any more states are there? How many? Have I counted everything? Okay, maybe this I should make bigger. 1, 2, 1, 2. I think I've counted all of them. What about this formula? 3 to the power 2 by 2 factorial, right? 3 to the power 2 by, which is 9 by 2, which is 4.5. V to the V is 3, 3 square by 2 factorial. 4. So that V to the power n by n factorial is not coming out to be a real number. So this formula cannot be right. So what can it be? N power v by n factorial. Let us substitute that by v factorial, n factorial. This is equal to 2 to the power 3 by 2 factorial. 8 by 2 equals 4, out. Not correct. There is a problem, no, that there are these 5 children standing and there are 10 apples to be given. How many ways can I give 10 apples to 5 children? VCN is definitely not going to work because VCN is 3C2, which is 3. We have to get 6. This is 6. 6 is the right answer. Whatever formula you give, you have to give 6. V factorial is not going to work because if I make n equal to 1, then I have only 3 ways, so that doesn't work. So, okay, so this problem we have all seen before. It is just stated in a different manner. So let us come back. So there are V sides, n indistinguishable particles, this is the statement of the problem. So what is the standard way of doing this? You take these n particles, you add V minus 1 partitions to them. Then you permute these partitions and the particles. So a particular configuration looks like this: particle, 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 partition, particle, particle, partition, partition, particle, partition, partition. All these particles I'll put in the first side, this in the second side, third side, fourth side, and last side. So that was the way of counting. This counting I have seen before. This is what I said: when you have n children and some apples, this is how you do it. So how many ways can I do this? There are n particles, V minus 1 partitions, n plus V minus 1 factorial by n factorial V minus 1 factorial, because these n balls are indistinguishable, V minus 1 balls are also indistinguishable. Okay. If I substitute 3, 2, 3 plus 2, 5, minus 1, 4, 4 factorial, remember 4 factorial by 2 factorial, that is 12, by 2 factorial 6, it gives this answer correct. Is this counting clear? Okay. So now there's another formula for omega, which is slightly different. But now we know what to do. Once we have omega, we do S equal log omega. But now it's a bit more complicated, this factorial. We use Stirling formula. So yesterday we used n to the power n plus 1 root 2 pi e to the power minus n. For this calculation, you can check that we need only n log n. Okay, you can, the half and all don't contribute. So I take the Stirling approximation for the numerator, n plus v minus 1 log n plus v minus 1 minus n log n minus v minus 1 log v minus 1. I forget about this minus 1 and so on because v is very large, or you can imagine that I replace v with v plus 1. So I have just dropped this minus 1, n plus v log n plus v minus log n log n. Okay. So now we have got an expression for entropy in terms of volume n. Energy is not there, energy is 0. All of them have equal energy. So the only differentiation I can do is with volume, del S by del V. So the first term n plus V and 1 by n plus V, that gives you 1. Then I differentiate this one, I get log n plus V. Then I differentiate this, nothing can happen. Minus V log V gives you minus 1 when I differentiate log V, and minus log V when I differentiate V. So I am left with, but del S by del V is P by T is log n plus V by V log 1 plus 2. I divide by V throughout, I get 1 plus rho. Rho is the number density. So now the problem is still non-interacting. I have just made the particles indistinguishable, and the equation of state has changed to something else. Instead of rho, I get log 1 plus rho. Okay. Okay. These are examples just to first of all familiarize with the law, and secondly to is nice calculation. But somewhere ideal gas must be hidden. If it was so dilute that particles are so far away, the non-interacting, it should become a non-interacting problem. So if I take the limit rho going to 0, then log 1 plus rho is roughly rho, and I get back ideal gas. Okay. So if you understood that problem, now let us make it a bit more complicated. Introduce indistinguishability and interaction. So previously it was non-interacting, distinguishable, then we introduced non-interacting, indistinguishable. Now let us make it indistinguishable and interacting. So let us make the most basic one sort of interaction, which is to say I have V sides, n indistinguishable particles, but they have a hardcore interaction, which means that maximum there can be only one particle per side. Two particles cannot sit on that side. Okay, so now I have made them really hard particles, so they cannot sit on top of each other. What is omega now? Sorry? VCN. Yeah, so he has given the answer as VCN. Does everybody agree with that? VCN. Huh? Does everyone agree with that? It just says that choose n sides from that VCN. Then there's only one way of putting them. The particles are not distinguishable from each other. They will not overlap, and that's the answer. What is the equation of state? So can you compute the equation of state for this? Okay, I can do the computation because I have done it here. Otherwise, so that is right. It is VCN. This you should just try out yourself. So now I repeat now I just do my machinery. S is log omega. VCN is V factorial by n factorial V minus n factorial. So I take logarithm of that. Log V factorial is V log V roughly. Other terms will not matter. Minus n log n minus V minus n log V minus n. Then I differentiate with respect to volume. When I differentiate, I get first term log V plus 1. This last one I get minus log V. Oh, there's a bracket here. And the answer is log V by V minus n. This is a simple algebra. So now I get pressure in terms of volume and this one, which is now log 1 minus rho. So now my equation of state has changed again to something else. P by T is minus log 1 minus rho. And of course, in the limit rho going to 0, I should get back ideal gas, which I do. Log of 1 minus rho is minus rho. So I get minus minus goes away and I get 2. Okay. So let us look at all the 3 equations we derived. P by T is rho, P by T is log 1 plus rho, indistinguishable, no interaction. P by T is log 1 minus rho, indistinguishable, hardcore. This is my ideal gas. This is my log 1 plus rho. It has to come below. For large rho, it is log rho. Log rho is much smaller than rho. It goes like that. This equation, when rho goes to 1, it blows up. Pressure goes to infinity because I cannot put more than 1 particle per side. So it is all have the same slope here and it blows up at this point. Okay. So now there's a nice problem here. What is the problem? How can I go from here to here? So this was allowing per side infinite number of particles. This one is allowing 1 particle. If I did 2 particles, 3 particles, 4 particles and so on, can I go from here to here? Okay. That problem, okay. So let me summarize what we discussed. Rule number 1, all microstates corresponding with a given macrostate are equally likely. Once I got that thing, I could immediately define what's the probability of a microstate. It is 1 by omega, where omega is a number of microstates. And then once I know omega, there is one particular formula that gives you a thermodynamic quantity entropy, k log omega. Once I get entropy, I can use my thermodynamics to compute everything. So this is the set of rules you have to follow. Okay. Now, quickly, what's the word for that? Assignment problem. Now, so we had done V sites, N distinguishable particles, hardcore interaction, but now I say you can have at most 2 particles per site. So previously we had done 1 particle per site or infinite particles per site. If I did 2 particles per site, can I count? So when I was 1 particle per site, it was VCN. When it's 2 particles per site, is it possible to count? So I have let me restate the problem. I have n V sites, n particles. At each site, you can have at most 2 particles. Is it possible to do? Anybody? Okay. It's not maybe it's not so easy to count. So if I ask how many, if there are 2 particles or 3 particles, maybe it's not easy to count them. But it may be possible to count them if I give you instead of rule 1, I give you rule 2, rule 3, rule 4. In one of the rules, it may be easy to count. Okay. So right now it's not easy to count. But let me give you a different problem then. What about I have at most 2 particles per site, but whenever 2 particles come on the same site, then the energy system is energy epsilon. So if there were, so I have a configuration where there is there are at most 1 particle per site. That energy is 0. If I have a configuration where there is 1 site, 2 particles, remaining 1 or 0, my energy is epsilon. This problem, can I find omega of E? Is the problem clear? Now so whenever things pair up, I give it energy epsilon. It could be epsilon could be negative, positive, but write down abstract epsilon. Sorry? VCN minus VCN.
VCN minus VC2.
But where is energy coming in?
Okay.
Somewhere energy should be there. Energy could be 1, 2, 3 up to 0, 1, 2, 3 up to many points. Is it possible to do this counting? if I do this now we have introduced not just hardcore interaction, we have introduced some other interaction of finite energy. Is it so? This exercise, I think, I don't know. Maybe it's doable. Maybe if we do this one, it will tell you something about this one, because it is also counting. Sorry. This first question, second question. So there is a configuration. So let me draw some configurations. So one of them is like this. One particle. There are three particles. 1, 2, 3. In another one, it is like this. And the third one, let's say it is like that. And one more. Yeah, just some random configurations. This has energy epsilon. This energy 0. This is energy epsilon. This is energy 0. If I had 4 particles, I might have a case where this was like this. Then this energy 2 epsilon. So now I have a system which has a finite interaction, some hardcore repulsion because I allow only 2 particles per site, and the indistinguishable. Can I compute my equation of state and energy dependence on temperature? Can I compute for this problem? So sorry, n by 2
CR into PCR. Almost maximum 2 particles can go ahead.
sorry, n by 2
CR into
C
R. Like summation or R.
R
VCR.
into VCR.
This goes over entire summation.
Yeah, but where is my energy?
Into outside. Like this is the total number of states that could be.
Okay, so in counting problems, how do you know whether you are right or wrong? You have to do a small example and check whether it is right or wrong. That's all. Don't choose 1, 1, don't choose 2, 1, but choose for 3, 2 or something. There will be a few cases to count, 6 cases 3C2, and if you count them, then that gives you should give the right answer for all of them. How will one do this? Suppose I say my total energy is E. How many pairs are there? If my total energy is E, how many pairs like this should be there? E means, okay, epsilon is equal to 1. If suppose I say E equal to epsilon, n epsilon. Suppose I choose my total energy to be n times small epsilon. How many pairs are there? N pairs should be there. Okay. Those n pairs, how many ways there can be in many sites. How do I choose them? Out of the V sites, I choose n of them, small n. In those small n, I have to put those pairs. Only one way I can put. So think like that. And then, so then you will get, I do not know, maybe you can get omega of E, comma V. If I sum over all energies, I get back this quantity. If I don't worry about what the energy is, then I get back the top problem, but it's as a summation. Omega of E comma V, if I sum over all energy, then I get omega of Vn, the top problem. So maybe that will help in, first of all, this might give you some interesting answer. Secondly, it might tell you how to do the top problem and so on. Okay. But now I will stop here. But I would like you to try some calculation. I was a bit fast in the calculation because I was doing on the slides. But you should just work out a few examples, because once you know how to do these calculations, the motivation for these formulas you can pick up when you do theoretical classes.